So it can be slower. Just wanted you all to know. Uh, I've changed the timing for other days. So on Tuesday, Thursday, and Sunday, we meet at 9:30 a.m. And on the other days, we meet at 8:30 or 8 a.m. I guess. Okay, just take a note of that. Yeah, just join in and make sure, I mean, when you want to just use this time for practicing your own questions, do that. But just have some dedicated time on your calendar. So if you want to use this as a dedicated time on your calendar, 2 hours, 2.5 hours every day, you can use that. Okay. All right. So let's get started. So it's fine. Um, all right. So let's take a look at this account merge once. Okay. We stopped at this particular question earlier. I will try to make it more uh, easier. So instead of using graph mode and all of that. So let's use all that. Let's say. So what we want to do is we want to have our emails here, right? So we can have so let's say you have email one, okay, and this email is going to be connected with another email of the same person, email two of same person. This might be again connected to email three for same person. Okay, this connection, although it shows an arrow, imagine there's no arrow there. This connection, this connection. So this is going to get be connected with each other. It's connected to this. So all of these are connected to each other. Okay. Similarly, if there's another person, then that another person is also going to have some emails now. So his emails, if he is having email one, he has his own email one. Okay. Call it email one dash. Then he is connected with another email two one dash. Okay. So these are two different people. They have their own names and everything. Okay. So what we can do is we can try to build something like this using the emails and the names that we have. Right. And one more thing we can do is we can have a dictionary where value is basically your email, okay, and key is the name. Okay? So every email name is going to be there. Email name. Okay, so this is to make sure that we have email to name mapping properly. Right? So first we'll try to build this, and then we'll at the same time we'll build this also. Okay, so let's do that. And after that, what we can do is this is going to be stored somewhere, right? So this is stored in a particular data structure, which is going to look something like this. So E1 is connected to E2 and E3. Okay. After that, maybe your E2 is connected to again E1, and then your E3 is connected to your E1 and E2. Okay. And then you have your E1 dash, which is connected to your E2 dash, and then your E2 dash is connected to again one. Okay, so we can have this kind of structure, which is going to be your uh, dictionary again. You can use this dictionary So we build this dictionary, and after that we'll parse over this dictionary, which is basically a adjacency matrix for this particular node or for this particular graph that we have. This graph is going to be not connected, so you'll have multiple disconnected graphs here. So let's try to build this. So what we have for name, for account in accounts. So we need to get the name of the account, right? So name is equal to account. Zeroth position is always going to be the name. Okay, and let's use the first email. The first email is going to be your account one. All right, and we need a map where you have email to name map, which is going to have your emails and the name of that particular person. So your email to name map for this guy is equal to your first email. First email is equal to name. So that's the email to name map that we're updating for that particular email. After that, we can have multiple emails for the same person. Okay, and we also need this particular uh, data structure where we are storing this information. Correct. So we'll call that as adjacency matrix or list. Okay, call it list format. And this is basically going to tell. All right. So this is my first email, and first email is if if your first email is not in your this list. Okay, although we call it a list, we'll just call it okay. Anyways, not in this, then we'll add it. We'll add this equal to empty because it is not having any children when we start out. Okay. After that, we'll go through all the remaining of the emails. So we'll call it emails. For email, just another email or the next email in your account and all the values which are after second value. So for example, if this we are parsing, these two were already passed. We want anything after this. So 0, 1, then anything after 2. Those are basically our next emails. Okay. So what we can check is, first of all, we want to append this next email. So this dot append. What we are going to append this next email. We're going to have that value. Okay. Second thing, if this email, okay, we are trying to build this thing. If this email is not present in that dictionary, not in this list, we are going to create similar to that. We're going to create this your email that you have, the next email that you have, right? Then you can do this here. This is your okay. This is your first email, and then you'll do a vice versa also, which is your email dot append your uh, first email that you have. Okay? So that you can build this properly. So your E2 should also have E1 in it. E1 will have E2, but your E2 should also have E1 in it and also have E3 in it. So this is what you're building. So you have this adjacency list, which is basically connecting your graphs. Okay. So this is your adjacency list, which is connecting the graph. So when we check this, we can do a print and check this. Email to name is we have to update that also because email to name, right? So this is your email, and your name is basically your name that is present here. Okay. You can print that. We can print the adjacency list to check if it looks properly as we expect it or not. Move this aside. So you can see here, this is your standard output. So this is your email address, and these are all the connected ones. Then you have next email address, and then you have connected ones. Okay. One thing which is missing, which is E3, is not present there only because E3 is not present in the second node. So your E3 is not present in this particular example. So there's no connection between E2 and E3, but there's a connection between E1 and E3, and you can use that connection. So there's a connection between these two. So this belongs to the same graph. You can easily use that information. Okay. All right. So once you have that information, next thing is we want to now pass through this whole adjacency list to create your answer. Okay. You have to create your answer. Your answer is basically going to be something which is like this: your name and then all the email addresses for that particular name. Okay. So let's build an answer. So answer to start out with empty. Then we're going to iterate through whole adjacency list. Okay. So let's for that's going to have key as your key email. Key email in the adjacency list. Let's take we have to keep track of the visited ones so that we know that we have already visited. Visited equal to set empty. We are not visited anything. All right. So if your key email is in visited, you have to continue. That means you have to ignore that particular key and you want to move on to next key. Okay. If it is not, then first thing you do is you add it to the visited. Dot add the key email to the visited. Okay, that's fine. Now let's get the values that are present for this key email. So for this key email and the connected emails, right? The connected emails for that key email in your adjacency list and your key email. All right. So connected email in your adjacency list of connect in your email. Okay. Because now you're getting the connected email. First thing you check if it is in the visited. Okay. Basically, if your connected email is in visited. If it's in visited, no. If it is not, then add it to the visited because you're visiting that particular email. Connected email getting added here now. You got the connected email added. Got the connected email added here. Okay. All right. Now let's build the answer. So your answer or your current person, basically your we need a name, right? So name is going to be used from this particular email to name thing that we have. So email to name, and you can just use the key email that is present for that particular person. Okay, so that's your email to name. You have your name, you got there. Okay, next thing you want is all of these emails to be appended there. So next thing you are going to do appending all the emails, correct? So in order to append all the emails, so you call this current person dot append. First thing we append is the key email to that. So that's the key email that we're appending. After that, we are going to append the connected email. So the connected email is also appended now. All right. And finally, you will append this current person to your answer. Okay. That's okay. One thing that we may have missed is we have to email the emails have to be sorted. Okay. So we'll get that. So let's do one thing. Let's take the current person name first. Okay. Current person name. So that's the name of the current person. And let's just call current person emails. So current person emails is basically empty for now. Then you are going to start with current person email dot append your key, current person email dot append connected keys. So you're going to append your current person name plus your sorted connected emails or current person emails. Okay, so that's your answer. Return your answer now. Check. So it works. We need the emails in the sorted manner. So what we did is we just created this data structure where we have this disconnected node, and then so for example we visited this. We add it to the visited. After that, we go to the next or connected emails, add all of them to the visited. Okay. Next time we go to even dash. Even dash is not present in the visited because it was not present in this graph. So it was never added to the visited. So we'll go to this and this is going to get passed again and we get the answer. Okay. That's how. Okay. It failed again with the same test case. So what's wrong with this? Well to name is present. The adjacency list is present. Use this test case. Gate is creating gate. Okay. So on this. That's good. We want to merge all of this together. So this 4 is not connected, but this 3 is connected to this, right? And then this 2 is not connected to anything. This 2 is also present here. But still, it is giving me this as an output. It is saying that this is. Okay, let's print our adjacency list for this and check what is happening. Print your adjacency list. So it says this is the key, the values. This is the key. These are the values. These are the connected values. Okay. So first you go to 0, 0. After that, you add it to the visited. So you add it to the visited. After that, you go to 3, 2. Both of these are added. Okay. After that, you go to 3. 3 is already added, so no need to visit. Oh, okay. 3 is already added, so it is not going to visit again. It will not visit any of the 3's children. Okay. That's why it's not getting it because it's connected to 3. So I went to 3. So 3 was already added to the visited here, because of which it never went to this particular case. So 3 is never going here. So because it was already added to the visited, okay, which is fine. We don't want to add it here. That's what it says. Okay. If we don't add it here, then what would happen? So we have 3, 2. Okay. Submissions are like this. Graph is equals email dot com. Visitor is empty. We want to go through the graph of the visitor. Then list. Yeah. Okay, so we want to do a BFS here. That's what they're saying. All right. So, okay. So when we are iterating through this, we have to do a BFS so that all the ones are or everything in this particular graph are visited at once. Okay. So let's do a BFS here. So BFS was missing here. Visited we added, which is fine. So let's create a queue because we want to do a BFS. We need a DQ for that. And first thing we are going to add to our queue is basically your first email, which is present your key email. Key email is added here. You add it to the visited. As soon as you add it there, your current person, you get the current person. You can get it here, or you can also get it outside just before adding it to the answer. Keep it simple. Let me make it a little bit. Okay. So we want to do a BFS here. Okay. BFS here. First, we get the queue, add the visited here. Current person emails. Basically, your email that you have. Either you can use that or going to do a BFS here, right? So BFS is basically while queue is not empty. Let me get rid of all this whole thing. So while queue is not empty, first thing we do is queue dot pop left. So you're going to pop the left item, which is going to be your current email. Is that okay? So that's your current email. Now we want to go through. Yeah, now we want to go through all the children of the current email and add them to the queue. Okay. So for us to go through all the children of the current email, for we have this adjacency list, which is having all the children of that current node. So, or we can just call it neighbors. Okay, neighbors in all the neighbors of that particular email. If neighbor not in visited, okay, if it is not in visited, then add it to the queue. Queue dot add, sorry, queue dot append. Append your neighbor into the queue and add it to the visited also because you visited it. Visited dot add your neighbor into it. Okay, and these are your current emails. Okay, whenever you add it, also keep track of them. That is fine, I think. Let me just think. If you have visited here, so you need all emails, basically all the emails are empty for now. We will start out with the key email present in them. Okay, so these are your all emails. All emails are basically here. Then whenever we add it to the visited, we append the all emails. We append the new email that we have seen for that particular same person. Your neighbor here in this case, because neighbors are basically your current person, you get the email, all emails. That's how we do BFS. So we did a BFS here. We were doing the wrong action. So we go through this node in a BFS manner. For BFS, we need the key one out. This is the basic BFS code. Not doing BFS was the mistake that we were doing yesterday and also again today. All right. Next question is convert a binary search. We can skip this one, or maybe let's just take a look at it. Okay, so we the question. Let me send the screen. Page. It's called the link. Sorry. That's the link to that question and the. So what is given to us? We are given a binary search tree. So we know what a binary search tree is. Binary search tree is a tree which is having left side is always going to be smaller than the right side. That's one. Okay. And you can think left pointer as synonymous to the predecessors and successor pointers. The doubly linked list. For circular doubly linked list, the predecessor of the first element is the last element. The successor of the last element is the first element. Okay. So we are given this binary search tree, which is 4, 2, 3, and all of that. You want to convert this into a doubly linked list using this particular node that is given to you. Okay. That's the definition of your node, left and right. Oh, sorry. This is the definition of your node. You want to return the node directly? Okay. You want to return the node in such a way. Okay. Uh, we want to transform this in place. So you have to update this particular root itself without having to use create anything else. Okay. That's one. So we are given this tree node, and then we want to convert this into 1, 2, 3, 4, 5. So if 4 is your root, okay, because we are going to start with root, right? Always. So if 4 is your root, then your okay, then your previous is 3 and your next is 5. That's fine. Previous is 3, but then you have 2 here and then you have 1 here. Okay, let's just check here. You can think of the left and right pointer as synonymous to the predecessors and successor pointers. Okay, all right. So everything on the left of 4 are predecessors, right? Because this is a tree. Sorry, this is a linked list. So before 4, those are all predecessors of 4. Okay, 4 is a successor of all of these points. So your predecessor should be your left tree. So before 4, you should all have your left nodes always. Before 4, you'll have all the left nodes. So these are all your left nodes. After 4, those are the successors. They should be your right nodes. So your 5 is the right node, so it should be the next node. Okay, that's one. Again, 1 is the predecessor to 2 because it's the left node in the original tree. 3 is the successor of 2 because it is the next node on the uh, tree here. Okay, that's right. Okay, so how do we build this? So in order to build this in place, correct? So we have to make sure we have to just update the pointers there. The values will remain as is. You have to update the pointers. Okay. So we want to update the pointers. Do we have to start from here or anywhere? Let's just check here. The explanation is basically saying uh, your 1 is, next is going to be 2. Okay. And next of 2 is going to be 3. Okay. And next of 3 is going to be 4. All right. Just think. Let's take this small part. Okay. If you were to update this small part, what are you going to do is this left and right, right? Okay. So this right, so for this particular tree, this is going to be a central node and these are going to be your left and this is your right node. Okay. Whatever answer you get from here, that answer is basically going to be the left of 4, and whatever answer you get from here is going to be a right of 4. Okay. So you want to solve it in a smaller parts first to start out with. So let's say you have 3 nodes and you solve for those 3 nodes, or maybe if you're just one node in that case. Okay. If you're just one node, um, then its parent can be either its next or its parent can be its previous also. So in this case, it is previous. If it is a left node, then its parent is going to be the next. If it is a right node, then its parents will going to be the right node. Okay. So what we can do here is, since we have this small sub graph, small subtree, we can solve for this, and whatever is answered, we can give it to the parent. Okay. So we solve for this small subtree, and whatever is the answer, we give it to the parent. Then we solve for this, whatever is the answer, we give it to the parent so that it can point its next pointer to there. Okay. So if that's the case, all right, what can we do here? We start from 4, go to 2, go to 1. Since we are at 1 right now, we cannot go anywhere else. Okay. So one, go one step back to two. Okay. Or we can start with any node actually. So let's just start with here maybe. If we start from here, then we go to the left. We see that there is 2 present here, and then we say next of this is this. Okay. So sorry, previous of 4 is basically your node 2. Okay. And next of 2 is, let's say, 4 for now. Okay. After that, from 2 you go to 1. Once you're at 1, you change the pointer of this next to, say, 1. Next of 1 is 2 because it is coming from the left side, right? Because it is left, so 1 next is 2. Okay. And 1 previous is your 1 previous is basically your, let's just think what's happening. We have started with 4. Left of 4 is 2. Okay. Right of 4 is, sorry, left is basically previous and right is next, right? So previous of 4 is whatever is the left. Okay. Next is whatever is the right. Okay. So we want to change it in case, right? First, let's write it down. So your left is basically your yes, your right is basically your next. Okay, those are the pointers that we want to change to. Okay. So when we start from 4, if we go to left, then it's correct. Go to 2, go to left, then it's correct. From 2, when we go to right, this node, this connection is incorrect. Okay, this connection is incorrect. So 3 should be pointing, the previous of 3 should be 2. That means 3 dot left should become 2. Okay, so 3 dot left becomes 2 because I'm coming from 2 here. All right, 3 dot left becomes 2. 2 dot next, whatever is this value, I have to put it back here. 2 dot next becomes 3. And then whatever was the value of 2 dot next, it should be assigned to the 3 dot next. How do I solve this? So we do a for loop here. So the way we go through this tree, you can go through BFS or DFS, anything is fine because we have to go to every node. We go to BFS, so we go to 4 first, then we go to 2. Okay, then we go to 2 to 5. Okay, then we go to 1. So maybe we'll have to do DFS because we have to go 4 first, then 2, then 1. After that, we have to go to 3. So 4, 2, 1, 3, and then 5. That is the sequence of DFS. So we go to 4 first, then we go to 2, then we go to 1, then we go to 3. Okay. So when we go to 4, update the pointer, which is correct. Should return the pointer to the smallest element in the list. Okay, that's fine. This linked list actually is sorted if you see, because this BST, when you convert it to doubly linked list, you'll get a sorted list. What is the use of this binary search tree? That's what I'm trying to understand. Why do we need? There is some usefulness of that binary search tree, right? Start from 4, we go to 2, we go to 1. Okay. When we create the connection, we check. So we start from 4. Start from 4. Go to 2. Go to 1. 4 to 1. After that, we connect. We connect right. After that, we go to 3. Check its parent. Another example. First of all, let's keep a pointer head. Okay. So head is you should return a pointer to the head is say loop for now. Okay. So you start out from there, and let's say you want to do a DFS. So for DFS, you need a stack. Stack is basically empty for now, and you want to add root there. Okay. While your stack is not empty, you need to do a different kind of a. So you start from 4. So first, let's get the node out. Node is equal to stack dot pop. You got the node out, right? And if node dot left, sorry, node dot right is present, then put it in the stack dot and node dot right. Uh, Stack dot left, basically left node that you added. Okay, now that's fine. So we are going to go one by one. What kind of traversal do we need? So we want to 4. Let's keep track of the previous node for now. Yes. Just keep track of the previous node just to know where am I pointing right till now. Okay. To start out, my previous node is none. I'm pointing to nothing for now. Okay. All right. If this is not none, then I have to do something. Okay. If that is none. Else, I have to just update this to a node. Okay. So let's say my previous node is now 4. I went to 2. Okay. Because I went to 2, I will check now if my current node, okay, current node dot value is less than my previous node. Okay, if my current node dot value is less than my previous node. So when I'm at 2, if this is less than my previous node, okay, less than or equal to, what is that? Let's check if the numbers in the nodes range in this, all the, okay, these are unique, so I don't have to worry about equal to signs and all. So if it is less than the previous node, then what we have to do is, what are the connection for this? So this dot next is equal to previous nodes, right? So node dot, no, I have to go through. If I break this connection, then I won't be able to reach here. Will I be able to reach there? Let me just think. So if I break this connection, it is already present in the node. It is already present in the stack. So it will anyways be revisited. Okay. So if it is present in stack, it is always going to be visited. Okay. So I go to 4. I say 4 dot next is nothing because it's not going to be the value. So when I have these two nodes. So 2 dot next has to be 4. So 2 dot right has to be my previous node. Okay, that's one. So my previous node is basically node dot right is equal to previous node. So 2 dot next or 2 dot right is the previous node because right and next are same. Okay, this node dot left is my previous node. Let's make it like this. Okay, all right. So this is I broke this connection. This is already in the stack, and this went here. Okay. After that, I got to 1. When I get to 1, I check is 1 less than my previous node, which is true. So 1 dot next becomes 2. Okay. 1 dot next becomes 2, which is fine. And 1 dot left remains as is, so I can ignore that. Okay. So 1 dot next becomes 2. When I go to 3, 3 dot next becomes 1. Okay. Okay. 3 dot next becomes 1, right? So we want to do in order traversal here. Has to be present in the middle. We go to 1. This is 1. We want to do in order traversal here. So this is what in order traversal. Before writing the left into there, let's do this operation. This is how you do in order traversal. Yes, node. Yes, that's fine. You check the previous node. Okay. So let's put the things in the stack right now. So let's start with this. Your stack is having only 4 present there. After that, your previous node is nothing, none. Then you went to 2, correct? Because you appended 5. So your stack is basically having 4. Now, stack is having 4, but you popped the 4 out. So your stack, this became out. Then your stack is going to have 5 and it's going to have 2 in there. Okay. And then you pop 2 out and your previous node is 4. Okay. Then you pop 2 out. Okay. Since you pop 2 out, uh, your current node is becoming your current node. Okay. 2 dot right. You add it to the stack. So you append 3 to the stack. All right. After that, you check 4 and 2 are these connections that you have here. Okay. 2 is less than 4. Okay. Dot value is less than 4. So 2 dot right should become your previous node. Okay. So 2 dot right becomes your previous node, which is fine. So 2 dot right becomes your previous node. Okay. After that, you append the left into the stack. You append 1 into the stack. Okay. Next, your node is 1. You remove 1 here. Your previous node is 2. Okay. You pop out here. Your current node value is less than your previous node, which is true. So your current node dot right becomes 2. So that's fine. And after that, you cannot append anything else to the stack. So you're done there. Okay. Next, your previous node is 1. Previous node is 1 there, right? Okay. So your previous node is 1 in this case. Okay. So if your previous node is 1, check the value. Then 3 dot next, sorry, 3 dot I need to ask help. Okay, how to traverse? We want to get the DFS. Got this right. The strategy we adopt the depth as the priority. So that one would start from root and reach all the way down to the certain leaf and then back to the root to reach another branch. Okay. can scan through DFS pre-order is node, left, and then right. DFS in order is left, then node, and then right. DFS post order is left, left, and right. This is BFS, which is node, left, right. Okay. Approach one, standard in order, which is what we are trying to do here. Where left and right are parts of recursion, and put it there. Okay. Initiate the first and last node as null. Call the standard in order traversal helper. Okay. So let's start with this. So we have current node is 4. Okay. So my current node is 4. Then we need a helper which is going to add 2 into the stack. So 2 is getting add it later. Okay. So you add all the nodes. So your current node, pick nodes, last nodes. Okay. Current node is this. The last node is this. Previous node or last node are basically same thing that we need. Just thinking. So how are they updating the previous node? So let's just do this. Okay. The previous node. Let's add the previous node here. Let's see what happens. Okay. So add the previous node here. Start with 4. Okay. Start out with 4. The stack is empty for now. Basically, your stack is having 4. The previous node is none. And then you popped, got 4. Stack became empty. Previous node is nothing. Your stack is going to have 5. And it's going to have 2 in there. Okay, that's fine. After that, you popped 2. The previous node is 4. Okay. You pop 2. The previous node is 4. Okay. Just think. So you popped 4. Sorry, pop 2. This node is 4. Then you create the connection, which is true. And then your previous node becomes 2. And your dictionary, sorry, your stack is going to have 3, 1. Okay. After that, you pop 1. 1 is popped. The previous node is 2, which is fine. How do I do this? How do I make sure that I keep track of this 2 as a previous node when it's popped? Think start out with keep track of the previous node. So in addition to the write, I also need to keep track of who is the parent of this. Let's try that. So we keep track of the parent and that node also. None. So there's no parent when we start out with this. So we don't need this previous node for now. So you can just keep track of the parent and that node. Get the node and its parent. Get the node and its parent. We add it there. After that, when we append 2 things. We append the node and then we also append its parent. Okay. Let's append this. For this. So we append the node and there. We don't need previous node here any longer because we are just keeping track of the parent. Okay, so parent is fine. So we just check the parent. Let's work. Okay. All right, so what we did here is we started out with 4. 4 is having nothing, no parent there. We pop out null, and then we just append 2 and 5. So you have 5 and parent is 4. Then you have 2 and the parent is 4 here. After that, we pop it out. So we pop 2 comma 4. Check the parent. Parent is the current node is smaller than the parent. So current node dot right is becoming my parent. It's becoming the parent here, and node dot left is basically parent when it is higher. Okay, that's fine. Okay, so then we go to 1 comma 2. When we go to 3 comma 4, let's check what happens here. When you go to 3 comma 2, where 3 is your node, 2 is your parent. Okay, take the value. All right, so node dot value. So you have greater. So the left of this is your parent. Okay. But 4 is pointing to, okay, left of this is parent, correct? Okay, so whatever is parents next, correct? Interesting. So whatever is the parent next, it has to point to the left of node. Okay. Left of this parent is fine. Then we want to keep track of parent dot right. Okay, and node dot right. Okay, so your node dot right is going to become parent dot right. All right, and your parent dot right is going to become node dot right. Your parent dot right is going to be this node, and your node dot right should become this guy's parent. This guy's right. This is what you want to do. Okay. What about this? So just check how far we got. At dot val is less than, or is greater than dot val, then head is equal to node. Okay. Let's just return node for now. Return head for now. Let's check what we got. We'll solve the whole problem, I guess. State stack dot pop. Node dot left. Why is it tiny decision? Along with this stack, pop the element, which I node dot right, and we add the right part. Node dot left only at the left part. So why is this going infinite loop? Because we are incorrectly pointing them. That's why. Hmm. So this is the case. Let's just update the rights also here. Let's update the left dot left dot left. Let's flat. Because of this pointers changing. Let's just check. Uh, I got approved. Not post. Post is equal to post class none class complete. Post. So dot left. Post. So last dot right. Node node. Node dot left. So we need two node filters, which is first and last. So we can small values. Let's do that. Let's try to here first, then we have last, which are point to none, none. Uh, if last is if last is not none, then last dot right is equal to current node, node dot left is equal to last. Okay. Else first node, last is equal to node. Okay. Let's try this. Okay, they are saying it. Then try to figure it out backwards. Once this is done, for that, um, last dot right is equal to first and first dot left is equal to last. And become first. Very limited feedback. Stack is storing too many things. So what is happening? So we don't need this. First of all, let's clean this up. Stack is empty. We don't need anything in the stack. Keep the right one. That one. Stack. Last dot right is equal to no. So last is not complete. Same error. Let's take help of ChatGPT. Okay. Current node, left and right. However, the transformation requires in order traversal left. Add left first. Okay. For in order traversal, this is how the in order traversal is done. You get all the way to the bottom, and then you get the current node. Um, where is the right getting added? This works. Try to understand. So nodes 4, sorry. This is the tree 4, 2, 5, 1, 3. Then if you stack, the current node is 4. Push 4, 2, and 1 all the way to the leftmost node. Okay. Stack is this. So current node is 1. Okay. Then you process 1. Set last dot right is equal to current. And current dot left is equal to last. Okay. So current is 1 and the right becomes 1. Process 2 from the stack. So in order, just go to the left automatically. Node. Okay, let's get back here. So we want to do the in order traversal. Have your stack. Current is root to start out with. What is the need of this current outside? That's what I'm trying to understand first now. Let's put the stack in there. That's fine. Let's do the current. Current is equal to stack pop. But stack dot pop is 2 times. We need the current outside that. Okay, so you need a current outside. This current is basically a stack. So as long as the current is empty, go all the way to the left. After that, you get the current node, and then you check if your last. So you check the last dot right becomes your current node. Okay, and your current dot left becomes your last node. Go to the description here. So this is your current node. After that, this becomes your current node. This is your current node. Your last node is this. Okay, so this is your last node, and this is your current node. Let's just check this particular code once again. The current is becoming current dot right. So last is only used to keep track of what was the last one that we traversed. Okay. All right. So let's try to understand this fully. Okay. So I think I've got hang of it. Just explain what I have understood from what I've seen. So in order to do in order traversal, first of all, the code that we're writing for in order traversal was wrong. The in order traversal code is the one that is shown here, okay, in an iterative manner. So for in order traversal, you need your stack, which is correct what we did. Then your current node should be a root. Okay. Then you add, uh, then you go all the way to the left. Okay. You go all the way to the left, the smallest to the last node on the left side. After that, you pop the leftmost node. All right. Process the leftmost node. Okay. Process the leftmost node and uh, current is equal to current dot right. But there is nothing on the right side. Current. Okay. No, man, this is something is wrong here. Because if this is true, just check here. Current. Oh, my stack is not empty, right? Okay, sorry. Go here. So yeah, so what is happening here is you go all the way to the left, but your stack is not empty. So if your stack is not empty, this is null. You pop your second item in your stack. So that is your parent. Then process the parent, and after that, your current becomes your the one which is on the right side. Okay, okay. This is how you write the in order. If you want to take notes, you can write this particular code, which is for in order traversal. Okay, this is good. Let me just give me a minute. I'll post it on the Discord channel. Uh, So for post order, you need two stacks. Uh, all right, so let me just send this code to you all. Want this right? This whole thing. Super. Post order. Okay. Pre-order. Post order. Get everything at once. Okay. Sorry, I'm also edit this. one should be the nodes. Start pointing to nodes. Second thing, should be related to the nodes. Also going to not sure how to get that. Okay, so check this in order, pre-order, and post-order traversal. Okay, so the one that we want to do is the in order traversal. So let's write the code for in order traversal for this particular. So for in order traversal, what we need is we need a current here. So obviously you can write it with an uh, recursive call, but I think I feel this is more straightforward than recursive calls, because here we can see the variables changing. If you write recursive, maybe you'll get a little confused. That's what I feel, but it's up to you. Okay. So this is an in order traversal. We need a stack for this, where we keep on pushing the items onto the stack so that we can traverse them. This is again DFS, depth first search. Current is your root. So we are going to iterate through the stack until the stack is empty or your current is not null. Okay. And then you go all the way to the left. Right? So you go all the way to the left. So let's take this example. So if this is the tree, you go all the way to the left. Okay. And then your current is basically your one right now. Okay. Then you process one. After processing one, what you say is current is equal to current dot right. Okay. So on the right side, there's nothing. Okay, on the right side, there's nothing. So current becomes null. Now, because current became null, you're going to pop next item from your stack. Next item from your stack is 2. So 2 gets popped. Because 2 is getting popped, you're going to process 2. Okay. You're going to process 2. And after that, you're going to update your current to current dot next. So now you're processing 3. So that's how you do in order. So now you process 3. So 3 dot next or 3 dot right is null again. So there's nothing on the right side of the 3. So you pop from your stack. So you pop 4 out. Then you process 4 and so on. So that's how the in order traversal works. That's the code of the in order traversal. Okay, you need you need two things, which is current and the stack. Okay, so let's do that. So we need to do in order traversal. Okay, so first let's write the in order traversal. Have a stack for that, and we also need current. Current is so while your stack is not empty. Okay, while your stack is not empty or your current is not null, go all the way to the left. So for that, while current basically you're 4 right now, so go all the way to the left. So you want to say stack dot append current dot left. Okay, and then you want to say current is equal to current dot left. Okay, now you pop the first item from the stack. So you update your current is equal to your stack dot pop. Your current is getting updated now. So this is what we are doing here, right? The current is getting updated. All right. So you pop the first item from your stack. That is your current item. Now let's process this. Process current. After processing current, you want to say current is equal to current dot right. So that makes sure that we move on to the right side of the tree. So your current becomes right side, and you want to pop the uh, parent back first. So this is how you do the in order traversal. Okay. This is your in order traversal. And what they're saying for this particular case, you want something called as last and first. Okay. So this last and first is basically used to keep track of how your parents are getting how your parents are getting how the parents of that particular node are getting reconnected back. Okay, so last first which are point to none to start off with. Okay, if your last is not null, Okay, if your last is not null, uh, your last is basically your current node. Okay. I think so. Let's try to use the model traversal here. So we start from 4. Okay. So 4 dot previous should be just take helpful. So this is your last dot right is going to be your current node. So your last dot right should be your current node. Okay. So 1 dot right should be your current node. Okay. All right. So your last dot right becomes your current node. Okay. So your 1 dot right becomes your 2 when you go to parent. Okay. After that, your last is your current right. So when you process this directly, pop this out. So last dot right becomes your current node. Okay. And current dot left should become your last node, right? That's what we are doing. Current dot left should become your last node. Okay. And your current dot left should become your last node. That will make sure you have all of them. And if your first is not null, or if your first is null, then your first is basically your uh, leftmost item that you have, which is your current node when you start out with, correct? So first is basically a leftmost item when you start out. Okay, it's not the leftmost item, but it's the smallest item. It should be the smallest item, not the leftmost item. Else, your first is current. Okay, so that your last dot next, your last dot right becomes your first, and your first dot left right. So that it becomes a circular list. And you return first one. Yeah. Appended current is fine. Not like current. Right is not defined. So we had to do in order traversal. Take notes from here for the in order traversal that I shared. Okay. Let's just quickly check this pre-order also. So for pre-order, the code that we were writing till now, actually that was for the pre-order only. I was making a mistake there. So we have a stack, which initialize route into the stack. Then we just keep on popping the item from the stack and just process it because it's an in order. First thing that we do is process the first item that was added to the stack, and it is the root node. And eventually you keep on adding left and right, and then you just do an in order. So first root, then left, and then right. Okay. Post order. This is different and looks a little bit complex at the first and on the outset. You have a stack, which is your first stack. In this first stack is you start out with root, then keep on iterating until your first stack is empty. Okay, so keep on iterating until your first stack is empty, and then you keep appending things into your uh, second stack. This code is very similar to your in order. So you see your in order traversal, sorry, in your post order traversal, your pre order traversal. Okay, check this pre order traversal code and this post order traversal. So there's everything is same. Only thing is when you pop, okay, when you pop this, you have to immediately push it into the different stack, which is stack number 2. So immediately put into stack number 2. Okay, and this is reversed. So this is right first, and here it is left first that you are pushing it. Okay, so here you're pushing right first and then the left, but here you're pushing the left and then the right, and then you just append it to the stack, second stack. After that, keep on iterating on the second stack. This is already going to be in the post order. Second stack is helping us doing the post order. Another way of doing post order is this other method that we discussed earlier, where we keep track of this visited stuff. Okay, we check the top. If the top is already visited, then we don't go here. Okay, we just go into this if condition, and we also have to make sure that our top is a leaf node first. Okay. That's what this is. We saw this code. We didn't see this other codes. This is post order code. This is pre order. That's the in order. Okay. Pre order code we already see. This in order is new one. Also the post order. Let's see if we can use it in one of the questions. Okay. Let's close this. Let's move on to the next question. Okay. So did longest increasing path in a matrix. So we do this. It is hard. Okay. Just think. All right. Let's give this a shot. It's going to take time. So let's just spend this. Reset. Start. So we are given a matrix, and this matrix is going to have numbers in there, and you may assume that outside of this we cannot go. Okay, wraparound is not allowed. So you want to find the longest increasing path in the matrix. So starting from 1 2 6 9, so this is the longest increasing path. Another increasing paths are this 1 8, this is second path which is increasing. Another increasing path is 1 6 9 or 1 6 8. That's also an increasing path, but that's not the longest. The longest one is 1 2 6 and 9. So this is the longest increasing path. Find out what is the longest increasing path in a given matrix. This matrix is of size m by n. That means you can have rows and columns that are of different sizes. Another example, 3 4 5 6. This is another increasing path. One more path here is 1 2. Okay, you strictly increasing equal रहेगा तो you cannot move. So this is 1, 6 is another increasing path. Then yeah, 3, 4, 5, 6. That's the increasing path, the longest increasing path. If there's only one, then the longest increasing path is just one length. So you have to return output as your which is the longest path. That is the output that you want to return. Okay. All right. So this looks to me like a dynamic programming problem because you want to get maximum. Okay. But can we also use any graphs here? Okay. So matrices can also be solved using the graphs. So because you want to find the maximum. Okay. One of the brute force way is start from here. Okay. Maybe start from here and then go. If you check what is the longest from here, there's longest one is just this one, so there's nothing longest. Go to this point and check what is the longest from here. Okay, go to this, check longest, go to this, check longest, go to this. So go to each and every cell and check the longest path. That is the brute force way of solving this. All right. We already know that we can move only 4 directions, so left, right, top, and bottom, and we can basically just check those directions, uh, basically move in those directions and get the answer if we try to do a brute force for each and every cell. Okay. Can we do better than brute force? Let's think. So we are given a graph here. So we know that the brute force is basically going to each cell and then reaching to its children and then just navigating through the graph until we reach. Okay. Uh, so we know from here, just one second. We know from here we can go to this. This is the longest path. Okay. When we go here, this is the longest path. Okay. Okay. So the longest path from here is basically 1 plus longest path from here. Okay. Longest path from here is basically 1 plus longest path from here. This is the higher number. Or it can also be this 1 plus longest path from here. But the longest path from here is basically just one value. So we cannot go longest anywhere. So answer for this is derived from these two cells, 6 and 2. Okay. Answer for this is going to be derived from these two cells, which are not present here. Answer for this can be derived from here. Is that true? What if we have 1, 2, 3, 4? So 2. Answer for this can be derived from here. Let's check the constraints. So size of n is 200. That is 200. So from here, I might navigate all the way. After that, here I might navigate all the way. That becomes n. And here, n. Okay. So each n into n, call it n. And from each cell itself, let's still add them to the same. N cube is 6. So force. Let's check this editorial. We need help. Okay, and that's all this one idea. So here what they're doing, they are going starting from each and every cell, and then they're going to solve what is the answer for that particular cell. They go and do the DFS for each and every cell, and it will give you the answer basically. So this is the brute force way of solving it. Now, the time complexity of this is 2 into 2 raised to the power m plus n. The search is repeated for each valid increasing path. The worst case is 2 raised to the power m plus n. Okay. Space complexity of n plus n. Okay. DFS with memoization. Memoization का मतलब होता है you store the result from a recursive call. So because this is a recursive call, right? So this is a recursive call. The DFS is calling again this DFS. This DFS is again calling DFS because the with the new input values. So maybe this was already solved. So this was already solved. We can store this result and then use it somewhere, use it later. Okay, that is what we this is called as DFS with memoization. Okay, one optimal way is to okay. Onion. All right, so let's solve this by first let's write the DFS, and after that we'll write the memoization part. Okay, let's get the directions right. So let's say to go through each and every node, right? So for I in matrix, so I in range, let's go to each and every node and try to find the maximum path length of matrix. For J in range, length of matrix 0. Okay. You want to find your answer. Your answer is, let's say, minus math dot inf. Okay. All right. So answer is equal to max of your answer, comma. We want to search to the whole thing. So we are going to search from matrix, send the matrix into the DFS, and this is a node that I want to start my search from. Okay. So whatever my DFS is going to return, and I'm going to return answer here. So let's write DFS function here. DFS. My DFS is going to need matrix. It will need x comma, sorry, it will need my x and y coordinates because that is from where I need to do my DFS. Right. Let's call it current node. Okay. So my current x and y. My current. Okay. We can write a DFS by using again that while loop, or we can also write the DFS using uh, a iterative method. Okay, let me just think what method would be right here. So we have current x and current y. Let's try to attempt to write it by using a iterative method. Okay. So what we want to say, we need a stack is empty when we start out with, and we need to send your send to here. So this stack is empty. Let's put current x and current y into the stack. Okay. Let's call it x and y for current x and current y. While stack is empty. This is DFS. We can again do in order, pre-order, or any of those. Okay. So let's just do a normal pre-order. So stack dot pop. Okay. So we want to do stack dot pop. Let's write the answer here. The max length. Okay. Max length path is to start out with is 1 because that is going to be your because you will at least have one node, right? So your max is 1. So this is your x comma y. Your x comma y, and you need to go through for all 4 directions, right? So let's write the directions also here. So I'll just write directions here. Directions is the matrix or the list which all the directions that I need to go. -1 is basically going to the previous column. same row. Okay. Maybe -1, diagonally up, then this is -1, same uh, row below above that, then this is 1, sorry, this is -1. We cannot go diagonal. We can go up, we can go right. Okay. Right, we can go left, sorry, bottom, which is 1, 0. Then we can go left, which is 0, -1. These are the only 4 directions we can go. Okay, so let's go for all the directions. For P in directions. Okay. Next X, next Y. Let's get that. Okay, X plus your D 0, Y plus D 0, D1. So your X and Y coordinates, right? Okay, that's okay. Let's just say what is your N and M. Okay, do that, or we can just clearly check it here. If next X, it has to be greater than or equal to 0, and it also has to be less than or equal to, for calling this X and I. So let me just make sure I get it correct. Okay, so we have this X, which is your, let's just call it row and column. Okay, because I'm more used to calling it row and column. Row, this is column. So that's the row and that's the column. This is your row, this is your column. This is your next row, next column. Okay, next row has to be less than length of matrix. Okay, and your next column has to be less than equal to length of matrix 0. Okay, that's also required. That's true. Okay, then you can move your then you can move to that direction, right? And also the value also has to be less than your current value, right? So your value of your next row and your next column has to be greater than your current row and current column. So your current row and your current column. If that is true, then if that is true, then you can move into that direction. Let's move into that direction. Then this stack dot append to append the next underscore R, next underscore C. Okay, so append that, right? And say directions plus max length +1. That's what we get. And just return max length. You can only go in one direction, so you don't have to worry about checking if it is visited or not. Let's check this. This is not defined. This is R. Let's see. Next R. Which one? Get out of index. Next R. Next C. We added that. This is going through all the values. That's your row. That's your column. What's wrong? Next row has to be less than matrix, not equal to, less than. Also output is 7, but expected is 417. Output here. The max length. What? Uh, check this question that is given to us. Is it correct? Let's just check here. Next, right? Then your current. Yes. Then right is correct. Um, if I move in that direction, then I cannot check next direction, right? Because I already move into that direction. So if I move into that direction, I cannot check next direction. So I have to break out from that direction. I take step in that direction, then I have to explore that direction. But uh, explore that direction, then so next direction will be added. So I need to check all the sides. If I move into that side, then I cannot update this directly because answer is basically max of two things, which is at every point I also need to keep track of my answer. So I need to keep track of my answer also. When I start out, this is my answer. Okay, it's my path length. That's my path length. So max length is equal to max of max length comma path length. So that's true. Just update my answer here. So max length is max length of that. And then this value, I just need to add this plus one here. Path length. So that should work. So the issue was I was updating my maximum length always. My max length will only get updated when my path length is there. The brute force one. So when I submit this, this is going to give me TLE, time limit exceeded. Hopefully it gives you. Alright, so we got a time limit exceeded. Now there are two ways of memorizing function. Okay, so what we can do is you can keep track of whether we have solved for that or not. Okay, so let's keep track of uh, solved. If you have solved for it, then don't solve it again. Get it from the solved array directly. Okay, and let's put it here like this. If our I comma j in solved array, okay, then don't solve it again. If it is not in solved array, if it is not in solved array, then solve for it. Solve I comma j and solve for it. Do a DFS and so give me the answer. Okay, and after that, whatever is the solution for that, use it here. So use the same solution back. Don't solve it again. Okay, if you have solved for this DFS for ij, which is not going to be true because you're not going to solve it, right? So the ing are always going to be unique. You are solving here somewhere. This is where the memorization is required. And if I use this, it's again going to give me time limit exceeded because this didn't add any value. Let's just think. What else can be happening here? Maybe I memorize this particular stuff. Maybe keep track of my solutions. Path length is already there. And when I pop this out, it is already solved. Then I don't need to do this again. If it is not solved, then I need to iterate. Okay, so the solved is not required here, but rather the solved is required somewhere else. Let's just fix that part. So we need the solved. It's empty for now. Okay. Solved. Second. Solved. Solve this. It's already solved. Sorry. Add this. So you want to add this solution. Add this solution. It's into max of both of this. You want to update your solution so that it's present. If is fine. I'm gonna memorize this part. This is not a recursive function. This is an iterative function. How do I memorize this iterative function? Okay. So my next. Uh, 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 how do I memorize this? So we need to keep track of the solutions that we are getting. So for R and C, that's the solution. So we don't want to solve for R and C again. Okay. So if we don't want to solve for R and C again, don't add it to the stack. All right, that makes sense. We should not add it to the stack. But if we are not adding that to the stack, How are we going to get the answer for that? Okay. So if it is already present, then don't add it to the stack. All right, let's do that. So salt for R comma C. This is uh, let's append. Sorry, let's add this to the salt. Okay, let's add R comma C to the store. That means we have solved for this. For it is set. Okay, right? And our next R and next C should not be the salt. If it is not in the salt, only then try to solve it again. Is this what you want? Says no. Some fails this. Expecting 140, but the answer is it passes these cases. But is that we solved and we make sure that we only check if it is not solved. Okay. But what about the answer for the solved one? So what if we keep track? Um, so we pop it out. So pop the maximum length out. Path length is maxed out. There's some silly mistake somewhere. So we have the solved and then we got the solved. Next next C path length plus 1. So small example. Small example. This example, if there is 7, it's this. The reason that it fails is because the output is smaller. The output is smaller because this stack that we're appending is not getting correctly. So what if we update our answer? So check this. That would be Solving it using the method. We'll have to go through this DFS iterative method. Okay, so let's do it. Let's write an iterative method for DFS. So we have a matrix, current C, current R. Go in all directions. Okay, our answer. We don't need a stack now because we were writing an iterative method. We need directions, which is for sure. We don't need the solved. Okay, we don't need iteration. So DFS max length is 1. Cache the output is the max length. DFS 1 next. No, this is not. To get the next R, next right. Don't need visited or solved. Uh, current C, current R. So it's basically your R. Basically C. Get your next next row, next column. Append it to the stack. All right. Not to the stack this time. Update your answer. So max length is equal to uh, max length is equal to max of whatever your max length is till now. Then we solve for next items plus 1 because we're moving to the next value, right? Solve for that. So in order for us to solve for that, so we need next R, we need next column, and this is direction. Sorry, matrix. Send the matrix into. Uh, so that's what we have. Your max length is that. When you start out, your max length is going to be 1. Yes. Okay, if there is a circular, why will there be a circular? Let's see, one which going to give you time. This will give you time. Let's just try this. So this work. So this is the data that you have. Okay. Now what they're saying is just keep a cache. That cache is basically going to keep track of your DFS getting called multiple times. Either you can use that or you can use function tools. Okay. So let's create a cache for now. Simple. Cache is an empty thing, and this cache is sent here, always. So we'll send cache in here. If cache is already having your RNC, if you have solved for this, then just return whatever the solution was earlier. Cache, return the cache R comma C. Right? Else, what we can do here is we can update our cache here this time. Cache R comma C equal to max return returns to the cache. Okay. Return the reference to the cache, we call the maximum. DFS is called. We have to solve it at least once. Store it in the cache. That's the value. This is how you memorize the recursive function. So we had a recursive function which was calling DFS again. And whenever you call the DFS again, it was resolving for the same solution that was solved earlier. So have a cache and store everything into the cache. That's continuous sum. Yes, not solved earlier. So continuous subarray sum. Alright, so we're given an integer array of nums and an integer k. Return true if nums has a good array or false. What's a good array? A good array is where its length is at least 2. So the length has to be 2 minimum, and the sum of elements of the subarray is multiple of k. That means summation of that is going to be multiple of k. Okay. 0 is always multiple of k. So that's fine. So we are given a target 6. Okay. So you have these numbers 23, 2, 4, 6, 7. Okay. When you take a summation of these two, it has to be a multiple of 6. Uh, it's not a good array. And the length also has to be at least 2. Okay. We have solved similar questions, but in that case, we didn't say it was a multiple of that. We just simply said, is it a sum of that or not? Okay, we had a value of k. Let's say it was 25. After that, you check whether it's a sum of 25 or not. Sum of a subarray becomes 25 or not. We solved that question earlier. Okay, this is slightly different. Here we are trying to find the subarray where the modulo has to be 0. Basically, summation of your window modulo with k should be 0. Okay, your window modulo with k has to be 0. Okay, earlier what you had, your window minus k has to be equal to 0. That's what you had earlier when we did the prefix sum. Okay, let's think if we can use the prefix sum kind of a thing. So when we were doing the prefix sum, we were storing, uh, first we were calculating the prefix sum, and after that we were iterating only through the prefix sum, and then we're storing something into the scene, right? So we are storing something to the scene where 0 was pointing to the 1 first. After that, we iterate into that prefix sum. So let's think if we can do something like that. Okay. Now there we were doing the prefix sum. All right. There we were doing the prefix sum, and just think. So prefix sum. Okay. So the prefix sum basically j minus prefix I is equal to prefix k. That is what we were trying to do earlier. Okay, so we want to say that this, or this is, sorry, window sum. Correct? This is your window sum. So we want to check this percentage k is equal to 0 or not. Okay, we want to check this. All right. So if we move the percentage on this side also, if we say percentage k, this percentage k will go inside again. Okay. All right. So this should also map. Okay, because modulo function is associative in nature. Again, you can send it inside and then it will still work as is. So we can take an example here just to make sure we understand it properly. So let's take this example where prefix sum until 4, which is 23 plus 2 plus 4, that is 29. Okay, so 29 minus, we have 23, which is the first sum, right? So 23. The answer is 6. And it is multiple of k, because it is multiple of k basically. Okay. Uh, Now, when we do modulo of 6, it's going to be 0. Okay. So modulo of 6 and then modulo of 6. So this is going to have a remainder of 6 5 is 35 minus, this is also going to have a remainder of 5. 5 minus 5 is equal to 0. Correct? So this matches. Okay. So this, when I do modulo, at that time also I'm going to get the same answer. Okay. All right. So since the modulus are also going to give you the same answer, inside your scene, instead of storing the prefix sum and the count, you can store modulo with the prefix sum. Okay, modulo with the prefix sum, and then count and then plus one, whatever that we try to do. Okay. So that will give us count, by the way, but we are not interested in count right now. So we are only interested if it is present or not. Okay. Let's get the prefix sums now. So we don't actually need to get the prefix sum fully. We can just keep track of the prefix sum by making sure that we have the current sum. Current sum is 0. Okay. And we need this scene, 0 colon 1. Okay. For n in nums. Okay. And then we have current sum plus is equal to n. That's what we have. Okay. Uh, Let me check if scene current sum minus k. Okay. Minus k. Okay. Let me just think. If the prefix sum is in scene. Okay. Then we have seen it. So we can return true from here. Right? Else scene current sum. The prefix sum till now. Okay. Percentage k. We want to store only the current sum. Plus is equal to 1. Okay. So let's try to do this. Is equal to 1. That's what we have. Okay. Now let's think. So percentage k. Okay. What do we need? So we need to check this is true. Okay. Current sum minus k. So if I move it here, then Just do this, right? Percentage k and percentage k, which is again going to be, because it's going to be 0, right? Because that's how it. The percentage k is 0. There's no remainder when you divide with k. Okay. Current sum minus k. Okay. That's what you want. Is this what is required? Return false. So that works. That worked because let's add two test cases. Okay. Let's add this test case and see what happens to. We have seen present inside scene. So or else return false. Expected false, return true, because length has to be at least, right? So since the length has to be at least 2, let's check here. So I have this one, and let's enumerate this. Okay, I comma n, right? Check. Uh, see, this is I. The length has to be at least 2, right? So window sum. So we are keeping track of scene, and when was it seen first? The 0 was seen minus 1 time. So just use that. Okay, so the index of that scene, whatever the index of this is basically, you don't have to write it like this. You can just write this. It will still work. We have to keep it consistent with what we have learned. I'm writing it like that. Okay, scene that. Okay, so now current is I minus, so 0 minus 1 minus, so 0 minus 1, that's my length, correct? So when I am at 0, present has to be my window size, okay, greater than 2, greater than or equal to 2. Let's use this. Wrong answer. Length has to be at least 2. That works. Use this. Let's check. 0, 0, 0. Okay. 0. Okay. We start out with 5. Here. Then you have 0. If it contains 0, I think you can just simply return uh, think. So if it contains 0, then what do you do? You have to handle the special case of 0. This is false. This is true. Windows sum is not increasing, right? So this current sum is not increasing when I add 0. That is what is creating problems. Windows sum is not increasing, but the length of window is increasing. So the window sum is not increasing, but the length is increasing. So while at page 3, we are expected to return. So we have 5000 value of page 3. So 3% is 5. So we have same test case. Test case. Why should we go on here? Because 0 multiplied by k or any number is 0 multiplied by any number is going to be 0. That is a multiple of k. 0 is always a multiple of k. Okay, so let's do this. If 0, 0, okay, if more than 2 zeros in your nums, you return to always. No, no, no. This is not 0, 0. 0 count, right? Just check. Counter of nums 0 in counter of nums and counter of nums 0 greater than equal to 2 than 1, you just return true. If I have more than 2 zeros, I have 1, 1. Like another help. Check structure but contains minor logic. Correct models on 0 and counter can be simplified. Goal is to track remainder using hash map to find the difference. So remainder is that remainder is negative. How will remainder be negative? Because numbers can be negative. In, then just check the length. Else remainder. Okay. What went wrong in our case? This we did correctly. Then we checked if remainder is less than 0. It was not in our case at least. Okay, let's try to see what changes are required in our case. Okay. If remainder is less than this, then we just need to add this one case. Remainder is seen. only set the first index. Let's just see so that we don't. Okay, fair enough. Let's try to check. So if remainder in C, if this is greater than or equal to 2, only then return true, and else only keep track of the current remainder. Okay, sorry, only keep track of the first time that you see that remainder. Okay, so that's fine. You want to keep track of remainder yourself. When is remainder becoming negative in this case? Let's show this. So this one case solved because we just did this check change. It will fail when the remainder is negative and the numbers are negative. Let's remove this. Okay. This is test case. That was not required. That's required. Okay. Right. Now let's see. It will fail at the negative. There are no negative numbers, it seems. It worked, but it would fail when there are negative numbers. There are negative numbers, then you have to check if the remainder is negative and then add this thing. Add negative. Add negative. If there are negative numbers, that's why it might happen. Okay. There are no negative numbers in our case, so we don't have to worry about it. We're there. Only thing that we missed is this part where we check. Okay, let's check if we can solve one more. Let's solve something that we have not solved earlier. Multiple strings. Yeah, what can something else. Lowest common ancestor of a binary search tree. Okay. Lowest common ancestor of a binary search tree. We have solved this one. Only thing is when we solved that, we knew who was the parent. We had one more node, which was the parent node, and we solved it using that parent node. Okay. Here we are not given the parent node, so we can solve it by the other method that we solved there, where we do a DFS all the way to the node, and after that we just pass it from the right side to get the answer. Straightforward. Lowest common ancestor of a binary search tree. Okay. This is the binary search tree, and that's the binary tree. The binary search tree, I think, it can be solved in log n. Nodes. Just about 10. Yeah, I mean, you can still solve it by using the same method. Even if you know that it's a binary search tree, you still find the path, and then you can use that same logic, which is going from the end of the list. So, for example, if you have this and you're trying to search P2 and 8, right? So your 2 and 8 are here. So you check all the way till 2. I went to 2 when I started from 6, and then I went to 2. And that's the path to reach 2. Path to reach 8 is 6, comma 8. I can get this path. Okay. After that, I can start passing from the left side. As soon as I see the common one, that is my lowest common ancestor. Both of them can be solved using the same method. kth smallest element in a sorted array. So sorted matrix, this matrix is sorted. K is equal to 8. Okay. So 159, 10, 11, 12, 12, 13, 14. So it's sorted. Find the 8 smallest. Yeah, I mean, this is because this is calling kth smallest. You can use max heap here, and let's just take the sizes here. Guaranteed to be non-decreasing order. K is less than k always. N is 300. Okay. So what this matrix is basically, this is a special kind of a matrix, which is having values which are like this. So you see, this is increasing from top to bottom, and if it's also increased from left to right. So left to right also it is increasing, top to bottom also it is increasing. Left to right is increasing, and top to bottom also it is increasing. And you want to find the 8 smallest, right? Mm, so since you want to find the 8 smallest or 8 smallest, you have to go through each and every node, then just keep a max heap. And anytime you see a bigger number, just yeah. So you can solve it in O of n, where you go to 1, add it to the heap because heap is empty. 5, add it to the heap because heap is empty. 9, add it to the heap because heap is empty. Then you go to the 8th highest, and then as soon as you go there, remove any value which is greater than that. So a straightforward solution for that. Can we solve it using something else? So let's try to solve it with that first. For I in length of matrix, let's call it row instead of calling it I. For C in length of matrix 0. Okay, we need a max heap here. An empty one to start out with. Push it to the max heap. As soon as you see the value, push it to the max heap. Q dot push. Okay, push it to the max heap. Push your value to the max heap, which is matrix 0, sorry, matrix R and column. So max heap, Python by default has a mini so that if length of your max heap is greater than k, then heap q dot heap pop. Pop from your max, okay? And then just return what you're like to pop from your max heap. Should solve the problem for us. So straightforward by using Maxi, but I think I don't think Maxi will be the, the use. So we want to use this sorted somehow. Okay. How do we use the sorted thing? Okay. Kth smallest, right? So we want to take k steps. Right? So when we are here, I have two options. I can go here or I can go here. Okay. let's say I take step this. Okay. Then I check the sides. Steps here. Let's say value of case 3. Let's say value of case 4. So you start from here. You take this size and this side. So now your value of now you're on the second node, which is the second and third highest node. Okay. One of them is second and one of them is third highest. So you go to third highest. Okay, you go to the third highest. From there you can go to I just skip the whole thing. Let's check this. Let's just minute or maximum. Solve it for other manual search. Think of it like okay, start from one. Yes, yes, okay. Count the number of elements to the left. Count the first. Search. All right, guys. I think we'll stop here. Let's continue tomorrow. We'll try to solve more questions. I'm hoping कि जब मैं solve करता हूँ तब आप भी बैठ के कुछ solve कर रहे हो, कुछ और पढ़ रहे हो या फिर कुछ तो. Okay, the time so that we can do it together. Okay. Bye everyone. I'll see you all tomorrow.